Thanks a lot, International Workshop on Modern Antenna Design and Challenges organizers for giving me this opportunity. Today I'll talk about performance metrics for MIMO antennas in MIMO wireless communication. I'm Professor Rakesh Singh Kshatriya from Indian Institute of Technology, Guwahati. First, I would like to acknowledge my students, Mr. Mohit Mishra, Dr. Sumanta Chaudhary, Dr. Anil Bowell, and Dr. Rajesh Kumani. I would also like to acknowledge my collaborators, Professor Alphonse, Professor Esele, then Professor Aisha, and Professor Cole. Here is the outline of the invited talk. I'll first introduce you to MIMO wireless communications. And this background is actually needed for analyzing MIMO antenna performance in MIMO wireless communications. So we'll introduce you to point-to-point MIMO wireless, where I'll discuss about diversity gain, rate of multiplexing gain. Then there's a trade-off between these two, which is called diversity multiplexing trade-off. Then we'll discuss about inter-antenna interaction. What is the interaction between one antenna elements of MIMO antenna with another antenna elements of MIMO antenna? The parameters we'll discuss are mutual coupling between antenna elements. Then we'll also discuss about envelope correlation calculation. Envelope correlation coefficient calculation. There are two ways of calculating envelope correlation coefficient. One is based from the scattering parameters measurement, and another is from the 3D radiation pattern measurements. Then we'll discuss about how to calculate antenna correlation coefficient. And antenna correlation coefficient can be calculated from the scattering parameter as well as from the envelope correlation coefficient. It is always wise to calculate envelope correlation coefficient from the 3D radiation patterns because it is highly accurate, and the envelope correlation calculation from scattering parameters is applicable only for highly efficient MIMO antennas. From the scattering parameters, you can calculate antenna correlation coefficient, and that is actually applicable only for lossless antenna. So all the existing antenna has some amount of losses, inherent losses. So it's better to calculate antenna correlation coefficient from the envelope correlation coefficient. So this is actually what we want to discuss in this talk. Section 3 will give you performance metrics of MIMO antennas and MIMO wireless. Section 1 and 2 are the background, which is necessary for discussion in section 3. So in section 3, we'll discuss about the diversity gain of MIMO antenna. First, we'll discuss about the array gain of MIMO antenna, which is actually called as mistakenly called as diversity gain of MIMO antennas in the literature. We'll discuss what is the issue with the array gain, and we'll define properly what is array gain, and it should not be actually called as a diversity gain of MIMO antennas. Then we'll discuss about the diversity order, diversity measure, percentage diversity gain reduction of MIMO antennas. We'll also discuss about multiplexing gain of MIMO antennas, channel capacity loss, and sum rate loss. Channel capacity loss is actually used in the single user MIMO, and sum rate loss is used for multi-user MIMO. Okay, so let's start with the introduction to MIMO wireless. So this picture shows single input, single output system. In the single input system, single input, single output system, we have one transmitting antenna at the transmitter and one receiving antenna at the receiver. So looking at the channel, it is getting input from one transmitting antenna of the transmitter and is giving output to one receiving antenna of the receiver. So single input, single output system. But for MIMO system, it will employ multiple antennas at the transmitter and receiver. There will be NT antennas at the transmitter and NR antennas at the receiver. So NT is the number of transmitting antenna, NR is the number of receiving antenna. Now looking at the channel, it will have input from NT antennas of the transmitter, it will have output to the NR antennas of the receiver. So multiple input, multiple output system. Okay, so what is the proposed matrix of any wireless communication device? So here we are showing many wireless communication devices. So what do we want in any wireless communications? As element, we actually want higher data transfer rate and less error in data transmission. Then how do we characterize performance of any wireless communication system? So there are three parameters here. First parameter is called channel capacity, which will actually discuss about the data transfer rate over the channel. So channel capacity is the maximum data rate one can transfer over the channel with minimum probability of error. As soon as we are transmitting at a data rate R, which is greater than C, which is channel capacity, we are in outtest. The probability of that is called outtest probability. And we can also find out how much error is there in the data transmission. This is called probability of error. So let us discuss about two gains Mimo wireless has. First is called rate gain or multiplexing gain. In the rate gain, we actually transmit simultaneously bits or symbols from the transmitting antenna, anti-transmitting antenna. Let us consider by taking 3x3 Mimo system. In the 3x3 Mimo system, let's say we want to transmit 3 bits, 0, 0, 1. 1 can be transmitted from the first antenna, 0 can be transmitted from second antenna, and 0 can be also transmitted from the third antenna. So we can have simultaneous transmission of 3 bits at a time when we consider 3x3 Mimo system. But let's consider a traditional wireless communication system where we have single antenna at the transmitter and single antenna at the receiver. We want to send the 3 bits like last time, but here we have one single link here. So we have to send 1 bit at a time. First send 1, then 0, and then 0. So the time it takes for CSO system to transmit 3 bits will be thrice of that of the Mimo system, 3x3 Mimo system. So there will be data transfer rate gain of almost 3 times that of the CSO system. This can be mathematically characterized in terms of capacity. So capacity for IID Mimo channel, IID means all the antenna elements as a transmitter, all the antenna elements as a receiver are independent of each other. It is quite possible if you keep all the antenna elements sufficiently far away. And you can orient in a proper direction, and you can also design it properly so that no antenna elements in the transmitter and receiver are interacting with the other antenna elements of the transmitter and receiver. For that, since we have antennas as a transmitter, in Mimo, we need to do power allocation over antennas. So the antennas, simplest power allocation is you apply same power to each and every antenna. In that case, every antenna will be getting PT by NT signal power. For equal power allocation for IID Mimo channel capacity has been derived in the literature. It has been observed that it is M times that of the single input, single output system, where M is the minimum of number of transmitting antennas or number of receiving antennas. It's interesting to look here. What is the capacity for the single input, single output system? In this single input, single output system, capacity is bandwidth times log 2 of 1 plus SNR. So if you want to increase the capacity for CSO system, you have to either increase the bandwidth or you have to either increase the SNR inside the box term. But for Mimo system, the increment in the capacity is without increasing the bandwidth and SNR. So SNR is, you cannot keep on increasing. There's issue of interference, and bandwidth is very precious. Once you decide what application, bandwidth is almost fixed. So Mimo actually increase capacity without increasing power and bandwidth, which is actually a very good thing for the Mimo because CSO cannot do that. So let's say you consider large scale Mimo system around M is equal to 100. Capacity for Mimo system would be 100 times that of the CSO system. Let us look at another gain from Mimo wireless, which is called diversity gain. In the diversity gain setting, we actually send the same bits from all transmitting antennas that will be received by all the receiving antennas. Let's consider a simple case of 3x3 Mimo system, and we want to send 0 bits. So 0 bits can be sent from the transmitting antenna to receiving antenna through different paths. For 3x3 Mimo system, there are 9 paths. So if any 2 of the links are down, 3 of the links are down, there's no issue here because bits can be received from the other remaining parts. So that is actually called diversity gain. Let's consider the CISO system, traditional wireless communication system. There we have one single link here. So if this link is down, we want to send 0 bits from transmitter to receiver. Receiver won't be able to receive the message bit which has been sent from the transmitter. So what is the advantage of that? Let us look at it from the perspective of bit error rate. Bit error is actually defined as number of bits in error divided by total number of bits sent. And it can be easily calculated. Let's say transmitter is sending 5 bits. Simple example, all are 0 bits. And receiver detect it as 11000. So how many bits are in error? 2 bits are in error. So probability of error is 2 by 5. Total bits in error divided by total number of bits sent. The probability error is 0.4. That's how we actually calculate probability error or bit error rate in wireless communications. What is SNR? SNR is a ratio of signal power divided by the noise power. So what is the advantage of this diversity gain? Let us try to understand. This plot here actually shows probability error versus SNR, CISO system and Mimo system. For the CISO system, slope is lesser. When you consider Mimo system, slope is higher. And let us take particular cases. Just before that, let's try to understand the expression for probability error for CISO system and Mimo system. For CISO system, it is 1 by SNR. For the Mimo system, it's 1 by SNR to the power diversity order or diversity gain. So obviously, when you plot probability error versus SNR curve, probability error for the Mimo system is going to have a higher slope. And because of that, we'll have 2 advantages. For example, for the same SNR, you actually want to find out how much is the probability of error or bit error rate. Typically, it will be around 0.5 into 10 to the minus 2. But if you consider for the Mimo system, the probability of error is around 0.5 into 10 to the minus 5. So for the same signal power, we are actually minimizing the error rate, probability of error. So the accuracy improves. Accuracy in data transfer improves. Let's look at it from another scenario. We fix the probability of error rate, and we want to see how much is the SNR required for that. You can see that for the CISO system, the SNR required is around 27 dB, whereas for the Mimo system, it's around 17 dB. So there is a reduction in the SNR required for Mimo system with respect to that of the CISO system. There's a SNR gain. This SNR gain is actually called as a diversity gain in the Mimo antenna literature, which is actually not correct. The diversity gain or the diversity order is actually decides the slope of the probability error versus SNR curve. But because of the improvement in the diversity gain of Mimo system over that of the CISO system, there is a SNR improvement. This SNR gain is actually called array gain. Okay, there is also a trade-off between these two. We actually want both of them to be very high rate gain as well as diversity gain, but you cannot simultaneously increase diversity gain and rate gain. Once you increase rate gain, diversity gain will reduce. So you have to design your Mimo system based on this diversity multiplexing trade-off. Let's say we have 5 by 5 Mimo system. We can actually use 3 antennas for rate gain, and you can actually use the remaining 2 antennas for the diversity gain. So diversity gain will be 4 and rate gain will be 3. So all Mimo systems should be actually designed using this diversity multiplexing trade-off. If you're interested in exploring about Mimo wireless, we have a book. This is actually my book on the fundamentals of Mimo wireless communication, published by Cambridge University Press, UK, and it is published in 2017. We also have another book on Mimo wireless communication over generalized spacing channels, co-authored by Dr. Brijesh Kumani. He's an assistant professor at IIT Ropur. So we know something about Mimo wireless communication, and two fundamental gains we have from the Mimo wireless communication. One is called rate or multiplexing gain, and another is called diversity gain. So we also need to know a little bit about what is inter-antenna interaction in Mimo wireless. Okay, so let's consider one antenna, and this radiation pattern is shown here. It's oriented in the horizontal direction now, and this is a standalone antenna. There is no inter-antenna interaction. Assume that there is another antenna very far away, antenna 2, with the diversity, with the radiation pattern shown here in red color, and it is also oriented in the horizontal direction. Will there be any inter-antenna interaction? There won't be any inter-antenna interaction because inter-element distance between antenna 1 and 2 is very far away. And they are also oriented in the horizontal direction. And there's no radiation pattern overlap. But let's say you consider another antenna 3 in between antenna 1 and 2 and is oriented in the vertical direction. Now there will be a lot of inter-antenna interaction between antenna 1 and 3. Whatever signal you're sending from antenna 1 will be received by antenna 3, and whatever you're sending from antenna 3 should be received by the antenna 1. So there will be a lot of inter-antenna interaction. And in practical antennas, it usually have back lobes also. In that case, antenna 3 will also start interacting with antenna 2. So the three most fundamental parameters for inter-antenna interaction is inter-element distance, orientation, and radiation pattern. So what is the effect of this inter-antenna interaction in the Mimo wireless communication? So this picture actually shows three antenna elements at the transmitter as well as at the receiver. And they're sufficiently far apart. There is no inter-antenna interaction. So this Mimo system would be able to give us 3 rate gain over the CISO system. But let's consider the same situation where your antennas at the transmitter and receiver actually have side lobes. There will be a lot of inter-antenna interaction. Because of this increased antenna interaction, the rate gain will be actually minimized. You consider another situation where your radiation patterns are overlapping for all the antennas. There will be a lot of inter-antenna interaction. So we will not be able to get the rate gain of 3 over such kind of Mimo system, closely packed Mimo system. And Mimo antenna elements of the Mimo system with side lobes because of this inter-antenna interaction. You can also consider the diversity gain setting where same bit is sent from transmitter to receiver. If the antennas are closely packed or inter-element spacing is reduced, you won't be able to get the same diversity gain of 9 from 3x3 Mimo system because of this increased inter-antenna interaction. So which parameter will actually characterize inter-antenna interaction? The most fundamental parameter is called antenna correlation coefficient. And before going to the antenna correlation coefficient, we'll actually discuss about 2 more fundamental parameters. One is called mutual coupling, and another is called envelope correlation coefficient. Mutual coupling, we should actually try to reduce it below -15 dB between one antenna element and another antenna element of the Mimo antenna. Similarly, envelope correlation coefficient is actually acceptable when it is below 0.5, but I think it should be revisit. We should revisit this criteria. Actually, ECC should be reduced less than 0.1, and most desirable should be around 0.0001. So we'll discuss that in this talk. Why should we actually revisit this value of ECC, acceptable value of ECC, which is 0.5? Our new acceptable value is 0.1 and desirable value is 0.0001. And correspondingly, you can also calculate how much is the antenna correlation coefficient which is acceptable and desirable, because antenna correlation coefficient can be calculated from the envelope correlation coefficient by taking its square root. Traditional antennas usually have single port and single paths, single radiator and single port. But Mimo antennas usually have multiple ports and multiple radiators. This is one radiator, another radiator. This is one port and another port. So this is a two port, two element Mimo antenna. So all the Mimo antennas usually have multi-port, multi-element. So the performance characterization of Mimo antenna is a little bit different from the traditional antennas. First parameter we use for characterizing Mimo antenna is called mutual coupling. Mutual coupling is actually measured between two ports. This is the vector network analyzer. It has two ports, port 1 and port 2. And we want to measure the mutual coupling between two ports of a Mimo antenna. This is a Mimo antenna we're considering. And how do we measure it on the left? We actually connect using coaxial cables to port 1 of the network analyzer to port 1 of the Mimo antenna, and we actually connect port 2 of the Mimo antenna with port 2 of the network analyzer. We send some signals from port 1 and measure how much is the signal received in port 2. So that is actually called mutual coupling between port 1 and 2. In terms of scattering parameter, that is also called S12. So that was good because we have only two ports, but many of the Mimo antenna has multi-ports. This one Mimo antenna we're showing here is having 6 ports. So then network analyzer has only 2 ports. How do we measure mutual coupling between different ports here? So it's a similar procedure here with one minor difference here, one minor or major difference here. Let's say you want to measure mutual coupling between port 1 and port 6 of the Mimo antenna. So you connect port 1 of the Mimo antenna with port 1 of the network analyzer. You connect port 2 of the Mimo antenna with port 6 of the Mimo antenna with port 2 of the vector network analyzer. You send signal from port 1, how much signal is received in port 6. That is called mutual coupling between port 1 and 6. But one point to be noted here, you cannot keep all the remaining ports open. You have to put math slot here. Otherwise, there will be a lot of reflection. You'll get a wrong result. Okay, so let us try to understand the formula for envelope correlation coefficient calculation from the scattering parameters. So this is the formula, it's given here. And what is the effect of mutual coupling in this envelope correlation coefficient calculation between port element I and J, or antenna element I and J? So you can see mutual coupling terms here in the numerator. So if you increase these values, mutual coupling values, then ECC is going to increase. Similarly, you have mutual coupling terms here in the denominator. This is 1 minus of something. So if you increase it, this value in the denominator will decrease. 1 minus something of the mutual coupling will decrease, and eventually it will increase the ECC. So if you minimize ECC, mutual coupling, you can actually minimize ECC from this simple relation you have here. Point to be noted here is that this formula is applicable only for highly efficient antennas, efficiency greater than 90%. So many of the antennas doesn't have that kind of efficiency. For example, you consider microwave antennas, which is one of the most popular antennas. Most of the time, microwave antenna has efficiency lesser than 90%. So there's another formula for calculating envelope correlation coefficient from the 3D measured radiation patterns. This actually tried to find the similarity of 3D radiation pattern of antenna element I and the antenna element J. And once you have this 3D radiation pattern measurements and calculate the envelope correlation coefficient, we can actually find antenna correlation coefficient as square root of envelope correlation coefficient. This is the procedure we'll be following in this talk, and it gives very accurate results. You can also find SCC or an antenna correlation coefficient from the scattering parameters by using this simple relation here. ACC matrix is equal to identity matrix minus admission of scattering parameter matrix multiplying with the scattering parameter matrix. You can easily find scattering parameters of Mimo antenna by making measurements in the left, and from there you can find the antenna correlation coefficient. But when we derive this antenna correlation coefficient relation on measure assumption is that it's a lossless antenna. So this formula is applicable only for lossless antenna. And most of the antennas have some kind of inherent losses. For example, microwave antenna has metal losses, dielectric losses. Dielectric resonator antennas has dielectric losses. So this formula may not be very accurate for finding the antenna correlation coefficient. But this is a very convenient formula because once you have scattering parameters, you can easily find what is this antenna correlation coefficient matrix. For 2x2 Mimo system or 2-port 2-element Mimo antenna correlation coefficient expression is given here. It's a very simple expression. So the fundamental question is, we have designed, fabricated, and tested a Mimo antenna. What next? Mimo antenna will be employed in the Mimo wireless communication. In fact, Mimo wireless communication cannot happen without antennas. Antenna is the heart of any wireless communication. So the question is, do we know what is the performance of this Mimo antenna in Mimo wireless communication? Or in other words, how do we characterize Mimo antenna's performance in Mimo wireless communication? So most of the existing performance metrics of Mimo antennas are not very useful for Mimo wireless communication. From Mimo wireless communication perspective, we should actually look at the Mimo wireless communication in terms of two gain. One is called diversity gain, another is called rate gain or multiplexing gain. So if the parameters which are there in literature is not very useful, we should actually come up with new parameters for Mimo antenna so that we can completely characterize performance of Mimo antenna in Mimo wireless communication. So that is the purpose of the section 3. The section 3 will actually characterize Mimo antenna in Mimo wireless communication. So these performance metrics are performance metrics of Mimo antenna for Mimo wireless communications. Okay, so let's consider a simple case of Mimo system. We have one single antenna at the transmitter, and we have multiple antennas at the receiver. This is called single input, single output system. And since the signal we are transmitting from antenna 1 of the transmitter can be received by multiple antennas at the receiver, antenna 1, 2 to antenna n, we can actually combine those signals which is received by multiple antennas at the receiver. Because of that combining we do at the receiver side, the SNR of the signal received at the receiver side is going to improve. So that is actually called array gain of Mimo system. And depending on what kind of combining scheme you employ, maximal ratio combining, selection combining, or equivalent combining, the performance, array gain performance of the Mimo antenna is going to change. So this is the outest probability curve versus SNR for selection combining over single input, single output, multiple output, ID Rayleigh fading channel. So the y-axis is outest probability and the x-axis is the SNR. So let us look at the outest probability for 1% outest. This curve is for the Mimo system and this curve is for the Mimo system. Mimo system employing two antennas at the receiver. So this 1% outest probability line is actually cutting the outest probability curve for the Mimo system and 1/2 Mimo system at different points. Let us look at the SNR, which is required for the 1% outage probability for CISO system and the Mimo system, 1/2 Mimo system. You can see that SNR requires 20 dB for the CISO system, whereas it's 10 dB for the Mimo system, 1/2 Mimo system. So there's a reduction in SNR required for 1% outage probability for selection combining over IID relay fading channel. How much is the reduction? How much is the reduction? Or in terms of SNR gain, we call it this as array gain. 10 dB SNR gain is there for the 1/2 Mimo system over that of the CISO system. And if you consider another case when you have 1/5 Mimo system, how much is the array gain? Array gain for the 1/5 Mimo system over that of the CISO system is around 17 dB, around 17 dB. So depending on how many antennas you are employing at the receiver, this array gain maximum is going to change. Why we are calling this as array gain maximum? We are considering it for the IID relay fading channel, where there is no antenna correlation between one antenna element and another antenna element. If there is antenna correlation, this array gain is going to reduce. So the maximum array gain for IID relay fading Mimo channel for the 1/2 Mimo system is actually 10 dB. Array gain actually reduced due to antenna correlation, so that amount of reduction is taken care of by the square root term here, square root of 1 minus ACC or square root of 1 minus ACC square. So the array can be defined as array gain maximum square root of 1 minus ACC or array gain maximum square root of 1 minus ACC square for a 2-element MIMO antenna. And for the selection combining over relay fading channel, array gain maximum is 10 dB. So array gain for selection combining over relay fading channel is 10 square root of 1 minus ACC, which is equal to 10 square root of 1 minus ACC square. So this array gain has been mistakenly called as diversity gain of MIMO antenna in the literature. Actually, diversity gain is the slope of the outage probability curve versus SNR. Array gain is the SNR gain because of selection combining or maximal ratio combining which is done at the receiver. They're two different parameters. Okay, so let's consider another case when you have maximal ratio combining. Array gain is going to change. We're considering IID relay fading channel, so that's a maximum array gain. When you consider MRC, then the 1% outage probability SNR gain for 1/2 Mimo system over that of the CISO system is 12 dB. So the maximum AG max is 12 dB for MRC, whereas AG max is 10 dB for the relay fading channel. So AG max keeps on changing for different fading channels. It has been observed for Nakagami fading channels also. This array gain maximum keeps on changing. So the 10 outside the formula for array gain, the previous equation, is not universal constant. It keeps on changing for different fading channels and different combining schemes. This is possible only when you have 1/2 Mimo system over IID relay fading channel. So for the MRC, the array gain for relay fading channel is 12 times square root of 1 minus ACC or 12 times square root of 1 minus ACC square. Even the array gain maximum for 1/5 Mimo system for MRC increases, is around 32 dB. It is different from the previous case. So you cannot say that diversity gain for MIMO antenna is always, maximum is always 10. This maximum for the array gain keeps on changing for different environment, different fading channel, or different Mimo system. So the conclusion is array gain maximum, which is taken as 10 in the MIMO antenna literature, is not fixed. It keeps on changing for different fading channels and different Mimo system also. So the second problem with array gain is that it becomes very problematic when the number of antenna elements grows. So this array gain maximum was actually defined for 1/2 Mimo system. So if you use that array gain expression, then square root of 1 minus ECC, what happens when we have a MIMO antenna with many number of antennas? N is much greater than 2. So MIMO antenna is employing multiple antennas as a receiver having N which is much larger than 2. And this is the usual trend. Number of antennas at the transmitter and receiver is increasing when we are going from one generation of wireless communication to another generation of wireless communication. In 4G, maximum number of antennas are around 10 antennas. For 5G, it's around 100 antennas or more. So number of antenna elements keeps on increasing. So the definition of array gain for 2 elements MIMO antenna is very cumbersome to use for large antenna arrays such as 100 elements. How many array gains you have to calculate for every pair of the antenna elements? It is decided by a parameter which is called NC2. N is the total number of antenna elements. Combinatorial of 2. We are selecting 2 antennas pair. For example, if you have 100 antennas, then we have to calculate 4,950 array gains. For one single MIMO antenna, we'll have 4,950 array gains. Let's say you want to compare one 100 element MIMO antenna with another 100 element MIMO antenna. In terms of array gain performance, we need to compare this 4,950 array gains of the MIMO antenna. This is really cumbersome, so not a good performance matrix. It doesn't actually give you a holistic view of the MIMO antenna diversity performance. Let us define properly what is the diversity gain of MIMO antenna. This is a N by N MIMO system. Transmitter is employing N antennas, receiver is employing N antennas. So we can define diversity gain in terms of 2-3 parameters here. First parameter is called diversity order. Diversity order can be calculated from the rank of the antenna correlation coefficient matrix at the transmitter and antenna correlation coefficient matrix at the receiver. When you multiply these two rank, you get the diversity order. There's another parameter who's called diversity measure. Diversity measure can be calculated from the trace of the antenna correlation coefficient matrix and the Frobenius norm of the antenna correlation coefficient matrix. And once you have the diversity measure for the transmitter antenna and the receiving antenna, you can actually multiply those two, then you get the diversity measure for the overall MIMO system. It's interesting to see, in order to compare performance of one antenna with another antenna, there's another term we can find out. It's called percentage diversity gain reduction. Ideal case, how much is the maximum diversity? It's usually the diversity order. And in the real case, when you have antenna correlation, diversity gain is measured in terms of diversity measure. So you can actually subtract those two, divide it by diversity order, multiply with 100, you get the percentage diversity gain reduction. So for the ideal case, diversity gain reduction percentage should be 0 and maximum is 100%. Let us consider a simple case of 2 elements MIMO antenna and find out what is the diversity gain parameters. You can see that antenna element 1 is having self-correlation of ACC1, antenna element 2 is having self-correlation of ACC2, and cross-correlation is ACC1, 2, and ACC2, 1. If you find the antenna correlation coefficient of antenna 1 and 2, or you find antenna correlation coefficient of antenna 2 and 1, they should be equal. And the SCC matrix for this 2-element MIMO antenna is SCC1, 1, SCC1, 2, SCC2, 1, and SCC2, 2. SCC1, 1, and SCC2, 2 are 1 because this is self-similarity of 3D radiation pattern of MIMO antenna 1 with itself, MIMO antenna 2 with itself. And cross correlation we can actually denote it by rho. That's a usual compensation people usually denote in the literature for the antenna correlation coefficient. So let us find out diversity order for this 2-element MIMO antenna and the H2. Diversity measure can be calculated from the Frobenius norm and the trace of the antenna correlation coefficient matrix. It turns out to be 2 by 1 plus square of rho. So you can find out percentage diversity gain reduction, which is 100 rho square divided by 1 plus rho square. Rho is the SCC between antenna element 1 and 2, and rho square is the ECC between antenna element 1 and 2. So once you know ECC, you can find out all these parameters. Let us do it for 2 elements MIMO antenna for the acceptable and desirable SCC values. In the literature, acceptable value of ECC is 0.5. When we find out percentage diversity gain reduction for this ECC, it is around 33.3%, which is quite high. So it is no longer an acceptable value for ECC. You should actually minimize it. Let's say if you consider 0.1 ECC, the percentage diversity gain reduction is 9%. So this is acceptable. So the acceptable value for the ECC 0.5 should be changed to 0.1. And the desirable value should be 0.0001. In that case, you can see that percentage diversity gain reduction is less than 0.2. It's 0.0199%. This is very good. So this should be the desirable value. And now just many antenna engineers are designing MIMO antennas with very low SCC values. 0.5 acceptable value is not acceptable. It should be revisited and it should be changed to 0.1. Desirable should be 0.0001. Okay, that's what for the 2 elements MIMO antenna. Let's go to n elements MIMO antenna. So here SCC 11 is the co-correlation of antenna 1, and SCC 22 is the co-correlation of antenna 2, and SCC NN is the co-correlation of element n. And cross-correlation between antenna 1 is denoted by SCC 12 or SCC 21. Cross-correlation between antenna 1 and n is denoted by SCC 1n or SCC n0. And cross-correlation between antenna 2 and antenna n is denoted by SCC 2n and SCC n2. Let us consider the equi-correlated SCC matrix. And in the equi-correlated SCC matrix, your diagonal elements of the antenna correlation coefficient of 1 of diagonal elements are rho. So we can calculate diversity order for this from the rank of the channel matrix, and it turns out to be n. And diversity measure can be calculated from this simple formula, n by 1 plus n minus 1 rho square. So we can also calculate diversity gain reduction. Percentage diversity gain reduction is 100 times n minus 1 rho square divided by 1 plus n minus 1 rho square. Rho square is the ECC and rho is the SCC. So you can actually do case studies. For example, when you increase the number of antennas, from 4, 8, 10, 15, and 100, how much is the percentage diversity gain reduction? Percentage diversity gain reduction is 60% when you have 4 antennas for the ECC value of 0.5. This is very high. So ECC value of 0.5 is no longer acceptable when you have 4 antennas. Similarly, if you go for 100 antennas, it's around 98%. It is almost close to 100%. So there is no any kind of diversity gain when you are having MIMO antenna with ECC value of 0.5 for 100 element MIMO antennas. There is no diversity gain. It's almost equivalent to that of the CISO system. So when antenna number grows, ECC value should be reduced. Let's consider another case when ECC has been reduced to 0.1. Antenna engineers design their MIMO antenna array such that ECC value has been significantly reduced to 0.1. How much is the percentage diversity gain for 4-element MIMO antenna? 23%. It's also quite high now. When you consider 100-element MIMO antenna, it is around 90.8%. So it's very high, close to 100%. So ECC of 0.5, 0.1 is not acceptable when you have large MIMO antenna array. So what is acceptable or desirable value of ECC when you have large antenna array? Let's consider 0.001. For the 0.001 ECC, you can actually calculate how much is the percentage diversity gain reduction for n equal to 4, n equal to 8, 10, 50, and 100. For n equal to 4, percentage diversity gain reduction is 0.02999. It's less than 0.03. It's quite good. So if you go for ECC of 0.0001, then your percentage diversity gain reduction is acceptable. Similarly, even if you go for 100 element MIMO antennas, percentage diversity gain reduction is less than 1, it's 0.98%. So ECC value of 0.0001 should be actually used for large antenna array. This is another case study. This is for several MIMO antennas we have carried out these case studies. First MIMO antenna we have considered is CP double plate monopole MIMO antenna array. There are two printed monopole antennas here in the form of circular printed monopole antennas. What we are doing at the ground plane of this MIMO antenna is that we are actually including some meta-grid lines here, single negative metamaterial structures. Because of that, there will be reduction in the mutual coupling between antenna elements, and correspondingly, ECC will be reduced. This is one of our paper in the IEEE axis, in early access. Because of that, you can see that there's significant reduction in the ECC. Here you can see ECC without the meta-grid lines is blue curve here is for the ECC without meta-grid lines. And the ECC with the meta-grid lines is also shown here. You can see that ECC with the meta-grid lines is always less than 0.026. This is quite good. This is a fabricated prototype of this DRA array. And we are still employing that meta-grid lines in the ground plane. We have actually shown that meta-grid line is effective in reducing mutual coupling of two-port printed monopole antenna as well as for DRA array. And you can see ECC for this case is also less than 0.046 throughout the bandwidth. And once you have ECC, you can fill up the SCC matrix for these two cases. SCC matrix is given here 1.161, 0.1611. This for the first MIMO antenna, two-port printed monopole MIMO antenna, and the second one 1.214, 0.2141 is for the DRA array. And we calculate the array again for this, for the relay fading channel. It turns out to be 9.94 for the first case, CPD with flat monopole antenna array, and it's 9.989 for the two-port DRA array. We have calculated the diversity measure as well as diversity order, and turns out to be 3.82 for the first case and 3.65 for the second case. Diversity order, you can see, is actually bound for the diversity measure. And the first antenna has higher diversity measure as well as array gain. That is because of the lower value of ECC for the first antenna. Let's consider 4 elements MIMO antenna case studies. We are actually using 4 elements MIMO antenna of the references shown here. And first case is for dual band PIFA MIMO antenna. Second case is for tri-band microstrip patch antenna. From the reported measure SCCs, we have ECC values. We have calculated the SCC matrix, and these are the two SCC matrices. From the SCC matrix, we can actually find out how much is the array gain, how much is the diversity measure, and how much is the diversity order. And this is 4 element MIMO antennas. So we'll have 6 array gain for every antenna. So the array gain for 4-element MIMO antennas are shown in table here in the second column, and diversity measure is shown in the third column, and diversity order is shown in the last column. So you can see that dual band mode PIFA has lesser diversity measure and array gain than the triple band microstrip patch antenna, which is a diversity gain which is much higher, and diversity measure is also 12.69, closer to maximum diversity order of 16. So this antenna, second antenna, will have better MIMO wireless communication performance in MIMO wireless communications. This is an 8-element MIMO antenna case study. This is actually one of the very recent paper which has designed 8-element MIMO antennas for the 5G smartphones. And from the ECC, calculated ECC values, we have filled out the antenna correlation coefficient matrix of size 8 by 8. Similarly, we have considered another 8-element MIMO antenna as a case study. This is a wideband low-profile microwave antenna designed for 5G mobile phones. And what is the diversity measure and diversity order for these two antennas? And it has been observed that first antenna is having diversity measure of 58.64. Diversity order is same for both the antennas because they are employing 8 antennas, and the rank of the SCC matrix is 8 for both of them. So we are employing 8-element MIMO antenna at the transmitter as well as at the receiver. So the diversity order will be 64 here. And diversity measure is 58.64 and 37.86. So the first antenna will have better performance in MIMO wireless communication. We have also done case study of 3 elements MIMO antenna, and we have found out PDGF for those cases. This is the SCC matrix for this 3-element MIMO antenna calculated from the envelope correlation coefficient reported in this paper, recent paper published in February 2022. And the rank of this matrix is 3, so diversity order is 3. And how much is the diversity measure? Diversity measure is 2.959354, and percentage diversity gain reduction is 2.15. So PGDR is quite low. So this MIMO antenna, millimeter wave trimodal MIMO antenna, will have very good diversity gain performance in wireless communication. Let's consider 4 elements MIMO antenna for PGDR case studies. Let's consider first scalp implantable MIMO antenna. This is for biomedical applications. And this antenna is actually very difficult to design. You have to implant it inside the human head. So, and because of that, they have a little bit higher ECC values. And there is another antenna which is wideband 4-corner fed square patch antenna, and this has slightly lower ECC values. This is actually designed for 5G mobile antennas. And we have also other case studies, 2 more case studies. One is MIMO DRA with complementary CP diversity, and another is PIFA pair-based MIMO antenna. Their SCC metrics are obtained from the ECC values reported in this paper. When we compare the performance, we see that the first one has the lowest PGDR performance. It has the highest PGDR performance. It will have lowest diversity gain performance. Third one, MIMO DRA1, will have best performance in MIMO wireless communication because PGDR is 1.96%, which is less than 2. This is all possible because third antenna has lower ECC values. So ECC becomes a major criteria for designing MIMO antennas, and if ECC values are lower, then MIMO antennas will have better diversity gain performance in MIMO wireless communications. And let us also discuss about the other remaining parameters which are actually related to the transfer rate. One is called multiplexing gain. Multiplexing gain can be calculated from the rank of the channel matrix at the transmitter and receiver, and minimum of the rank of the antenna correlation coefficient for the transmitter or receiver will give us the multiplexing gain. Our channel capacity can be calculated, and you can find out how much is loss in channel capacity due to antenna correlation, and it is minus log 2 of determinant of antenna correlation coefficient at the transmitter minus log 2 of determinant of antenna correlation coefficient at the receiver. And the point to be noted is this formula is derived when number of antennas at transmitter and receiver is equal, so you cannot use it for other cases. So let's do some case study. Case study 1 is for the traditional MIMO wireless communication, or let's say traditional antenna array, which is also called as equidistant antenna array. And for the equidistant antenna array, all antennas are placed in vertices of a equilateral triangle. Let's consider that case 3x3 MIMO system, point-to-point wireless communication. How much is the multiplexing gain? Multiplexing gain when you have ECC is equal to 0.5. It's a 3x3 MIMO system, and antenna correlation coefficient for equi-correlated case when you have ECC is equal to 0.5 is given here. Where employing identical antennas at the transmitter and receiver, channel capacity loss is 4.4218. It's quite high. So it's not desirable. You need to reduce the ECC value in order to have lower value of the channel correlation coefficient. Multiplexing gain is 3 because rank of this matrix is 3. This is all right for 3x2 MIMO system. And let's consider another simple case when you have circular antenna array with 4 antenna elements. And that is data transmission from transmitter to receiver, and this is single user MIMO or point-to-point MIMO wireless communication. So you can actually find out the antenna correlation coefficient for a circular matrix. This is a typical value we are considering for a 4x4 MIMO system, and you calculate the channel capacity loss is 4.3168 bits per second per hertz, which is also quite high. You need to minimize the envelope correlation coefficient. Multiplexing gain is okay. It's 4 for the 4x4 MIMO system. Let's consider 5x5 MIMO system where we are employing linear antenna array at the transmitter as well as at the receiver with 5 elements. The antenna correlation coefficient is also called exponentially correlated MIMO channel model, exponentially correlated antenna correlation coefficient. And when we calculate the channel capacity loss, it's quite high, 7.714 bits per second per hertz. So we need to minimize the channel envelope correlation coefficient to minimize the channel capacity loss. Multiplexing gain is 5, and it's okay for a 5x5 MIMO system. These are experimental studies. Those 3 cases we consider were theoretical studies, and we have actually assumed antenna array for the most widely used antenna array, circular array, linear array, and equidistant antenna array. So these are actually for the experimentally fabricated MIMO antennas. We're considering 2x2 MIMO system, and we're considering the MIMO antenna with the neutralization line here. You can see that in between the 2 patches here, you have a neutralization line, which will actually minimize the mutual coupling between the antenna array. And because of that neutralization line application between the 2 elements of the MIMO antenna array, ECC is less than 0.06211. So you can fill out the antenna correlation coefficient matrix now and find out that CCL is around 0.1847, which is quite low and very good performance. Multiplexing gain is, in this case, there's a typo here, it should be 2, and it's quite good. Okay, so let's go to the multi-user scenario now. So you see that in mobile wireless communication, there are many users which is actually served by base station. So most of the wireless communication nowadays are multi-user scenario. Let us consider one such situation where your base station is actually serving many antennas, many users, and we have K users here in the home cell of the base station. So here the communication is a little bit different. Whenever mobile phone is sending signal to the base station, we call this as uplink, because mobile phones are at lower elevation and base station is at a higher elevation. When you're sending signal down from the base station to the mobile user, we call this as downlink. Because of that, there will be two kinds of channel capacity. One is called uplink sum rate, another is called downlink sum rate. Because of the scenario we're considering multi-user, we actually sum the capacity of all users. So that's why sum rate. Sum rate will have two cases, one for the uplink and one for the downlink. So we do not have only one channel capacity here. We have two channel capacity, one for the uplink and one for the downlink. And here we usually call this as sum rate because we're summing the rate of every user. So let us consider such kind of scenario where we have M radio ports, and every radio port is employing NT antennas and base station is employing NR antennas. We want to actually find out channel capacity loss, which is also called as sum rate loss, especially for the uplink. It can be found out from this formula, sum rate loss for multi-user case. And here in this formula, TR denotes the trace of a matrix, M is the number of radio ports, and T is the number of transmit antennas for every radio port, and overall channel matrix we are considering is RT for all users. So let us do some SRL case study, some rate loss case study for the uplink. We are considering the same antenna we have used for 2x2 Mimo system in the previous case study, and we are using this in multi-user scenario. We consider three users here: user 1, user 2, user 3, and user 1, 2, and 3 are having Mimo antennas with two elements, and base station is employing NR antennas. This antenna is actually taken from our recent paper in the URSI General Assembly. Let's consider in a case where your base station with NR antenna is giving connection to two antennas, simple case, two users, and every user is employing four antennas. So the 5G terminal here has provision for employing more than one antenna, and we're considering the case for two antennas. In the previous case, we're considering four antennas for this case. So these are actually designed by this author here. You can see the references, and they are actually using four antenna elements. Looks like inverted antenna. Four of them are there. PIFA, four of them are there. So we can actually fill up the SCC matrix from the calculated Untitled correlation coefficient of the Mimo antenna for the case study 1 and 2, and we can compare the performances. Similarly, you can also consider case study 3, where instead of using four antenna or two antenna, they're employing 8 antennas at the mobile phones, 5G smartphones. We want to actually find out how much is the sum rate loss for this kind of scenario. Two users with 8 antenna elements for the uplink case. Similarly, we also consider another 8 element Mimo antenna for two users, uplink case. Let us compare their performances. For the 2x2 single user Mimo for SRL case study, we have already calculated maximum multiplexing gain was 2 for the CISO system, for the single user system, and WSTO was 4. Channel capacity loss are 0.0925 bits per second per us. This is what we have for single user case. Let us try to compare this with the multi-user case. In the multi-user case, first case, second case, third, and fourth case, And you see that first case employed two antennas at the mobile user. And let us assume that base station is employing 10 antennas for all cases. And we assume that there are 3 mobile users. In that case, we find the multiplexing gain. Multiplexing gain is 6. Diversity order is 60. And some rate loss is 0.0001 bits per second perhaps. If you compare this with the single user case, the multiplexing gain is 3 times that of the single user, and diversity order is 15 times that of the single user case, and channel capacity has been reduced significantly. So you see that when you consider the multi-user scenario, there is always improvement in multiplexing gain, diversity order, and some rate loss. So that's one of the reasons why people has gone from the single user to multi-user MIMO, especially in 4G wireless communication and 5G wireless communication. If you consider case 2, 3, and 4, case 2 is employing 4 antennas, case 3 and 4 is employing 8 antennas. So look at the multiplexing gain when you go from 4 antennas to 8 antennas. Multiplexing gain is double, 16. How about the diversity order? Diversity order is improved 2 times, 80 to 160. And if you look at the some rate loss is actually decreasing when we go from 4 antennas to 8 antennas, or let's say when we go from 2 antennas to 4 antennas and 8 antennas, even the some rate loss is minimized. So from the 4G to 5G, multi-user MIMO has moved from multi-user MIMO to the massive MIMO. The major difference is that in massive MIMO, there will be more than 100 antennas at the base station. The number of antennas at the base station grows less. Because of that, there will be huge improvement, especially the processing which is done at the base station is severely reduced. It is scalable because of channel hardening and favorable channel condition when your number of antennas at the base station grows. And what is the basic idea about, moving from single user to multi-user? It can be often from here. You consider the single user case point-to-point communication link first. So in the point-to-point communication link at the terminal, the inter-element distance is very low. But if you consider the intermobile user, distance is much larger. So let's say if you distribute the antennas of the terminal to mobile users one by one, then inter-element spacing increases, so diversity gain becomes huge, and people usually call this as macro diversity at the user side. And for the co-located antenna, there was micro diversity. So because of that, performance is going to improve for the MIMO wireless communication when we go from multi-user MIMO to multi-MIMO, as well as single user to multi-user MIMO also. So this is a simplified explanation of why do we need to go for a technology which is called cell-free massive MIMO. Cell-free massive MIMO is actually a technology proposed for MIMO wireless communication in beyond 5G and 6G wireless communication. So now let us try to look at one of the inherent problem in the cellular communication. You can see that there are many cells here. 5 cells are shown here. Every cell has a base station. So let's consider one user at the cell S. And it's in the home base station of cell 1. What can you observe is that distance between the base station antenna of the neighboring cells is actually quite close. It's even closer than that of the distance of the base station antenna of the home cell 1, because it's at the cell S is very far away from the home base station, but it is very closer to the neighboring base station of the cells 2, 3, 4, and 5. So the problem is that it will actually pick up signals from the neighboring cells, which are actually interfering with the desired signal which has been sent from the home base station antennas. So this term here, intercell interference, will increase. So SINR will actually reduce. SINR is calculated as signal power divided by desired signal power divided by noise power plus interfering cells or interfering user signal. So for the user cell is intercell interference power increases, so SINR decreases. What happens to the capacity? Capacity is log 2 of 1 plus SINR. Capacity decreases. So this is an inherent problem in the cellular communication from the beginning, and this is called near-far problem. Very near to the interfering cells and very far away from the desired cell. And this is unsolvable if you consider multi-cell cellular communication. So there's a proposal which is called cell-free massive MIMO, where they have actually completely removed the idea of cells. There is no longer any cells here, which is actually proposed to beyond 5G and 6G wireless communications. Let's try to understand that. So for the massive MIMO, you have co-located antennas at the base station, and the inter-element spacing is very small, and you have micro diversity here. But let's say you look at the access point here, access point 1, 2, 3, 4, and so on are very far away from each other. If you distribute antennas of all the co-located base station to access point, then inter-element distance actually increases, will have macro diversity. So when we move from single user to multi-user, there was macro diversity at the user side. So now base station is replaced by many access points, so we'll have macro diversity at the base station side also. Because of that, there will be a lot of improvement in the performance. And another thing is that here we don't have any cells. The concept of cell is completely free. We have many access points, so at any particular instant of time, any user equipment will be surrounded by many access points. So this user equipment actually communicated to the nearby access point, and the nearby access point will give very good service to the user. So all the geographical areas will be surrounded by many access points, and at any particular place or location, user equipment will be always surrounded by access point. So user will get best benefit out of this. It is always surrounded by access point at any particular time or space. So it will be getting the best service from the nearby access point. So this is called user-centric approach. User is at the center, and based on the user's requirement, what is the performance required by the user, it will be always served by the surrounding access point. In the previous cases, what we have was network-centric approach. Depending on the network ability and network service, user will get the communication. But here, it is called user-centric approach. User will be always surrounded by access point. And this is the seminal paper in the IEEE transaction of wireless communication by Professor Eriksson, Professor E.G. Larson, and Thomas Marzetta, and other co-authors. They actually compare the performance of cell-free massive MIMO with the small cells, and they have observed that user-specific experience will be much better for the cell-free massive MIMO. Anyway, so the performance matrix of MIMO antenna in the cell-free massive MIMO, which is a new technology, is not characterized. So it's an open problem. Okay, that's all for this talk. And if you have any questions, please feel free to ask.